going to look at the geometry of linear transformations and how to find the standard matrix for the transformation. The standard matrix being the matrix with respect to the standard basis. And we're going to go over some basic transformations. And we're going to specifically look at part 2, transformations of the plane. And maybe even some transformations of space. Okay. So if you have a linear transformation, if you want to find the matrix, right? So if you have a transformation that does something that's linear, you want to find the matrix associated to this transformation. So multiplying by a vector by that matrix accomplishes the transformation. So given T, find A. And the key is, well, there's several ways, but one basic formula is this one. If you know what the transformation does to the standard basis elements, you know the matrix. Right, so in R2, we want to know what the transformation does to the first basis element, and then to the second, and the results become columns of our matrix. And in R3, you can extend this pattern, and so on. Okay. So we're going to look at some basic transformations. Okay. So I guess let's start with rotation. R2. Okay. So if I want to rotate the whole plane by angle theta counterclockwise, so that's the positive orientation in math. What's the matrix that accomplishes that? Well, let's look at R2 and find the matrix that represents that rotation by first seeing what happens to the first basis element, the standard basis element. So we're going to take the unit vector that's pointing in the positive x direction and then rotate it by angle theta counterclockwise. Now this is a unit vector, right? So when we rotate it, we haven't changed the length. So this is still length 1. And so the resulting vector you get using trig, what would be the x component of that vector? I mean, you're all familiar with this, like using polar coordinates and so on. And y would be opposite to hypotenuse u sine. So apparently, the rotation takes this unit vector and turns it into a column vector cosine sine. So now let's check what happens to the second standard basis element. So that's a unit vector pointing this way, in positive y direction. You rotate that sucker 90 angle theta. Okay, and then we can draw a right triangle, and then we can see that the x component is negative in this picture, right? And it would be given by sine of theta. Negative sine of theta. And the y component is positive, and that would be adjacent to hypotenuse of cosine. So the transformation takes that standard basis element and gives you negative sine cosine of theta. So how would you then come up with, is this matrix invertible? Yeah, sure. What's the determinant? Cosine squared minus a negative sine squared. So cosine squared plus sine squared is 1. The determinant is not 0. This matrix is invertible. As you expected it to be, because right the range of this transformation is all of R2. So, and so how can you find the rotation by angle theta in the clockwise direction? So that's considered the negative orientation in math. Well, you can do one of two things. You can say, well, this is simply the inverse, or the undoing of the rotation by theta counterclockwise. Or you can simply use this formula and replace theta with negative theta. Right, we're just rotating by a negative angle. So, and then we can take advantage of the fact that cosine is an even function, so cosine minus theta is just cosine of theta, while sine is an odd function. So you get sine of minus theta is the negative sine of theta. And you can directly confirm that if you compute the inverse of this 2 by 2 matrix, you should get this. Yeah, I mean, you're just switching the diagonal. The determinant is 1, so 1 divided by the determinant is 1 divided by 1. Switch the diagonals, change the sign on the off diagonal entries. So how about if transformation, so let's just go through the kind of basic ones. What if I want to reflect, this is going to be a reflection about, say, x-axis, right? Because that's a transformation. So what would the matrix, standard matrix for the transformation be? And you can find out by simply seeing what the reflection about the x-axis would do to the standard basis elements. So let's find the matrix. So the first standard basis element, once you reflect it about the x-axis, what does it become? One zero. Reflected by the x-axis. It stays on that x-axis, right? And, so. Okay, what about the second standard basis? You reflect it about the x-axis, you get not too hard. So you get 0 negative. So there you go. There's the standard matrix for a reflection about the x-axis. What about if you simply want to scale? What's the determinant of this matrix? It's -1. So that's interesting. Okay. Well, it relates to these transformations and what the determinants of those transformations are.
You want another color?
No, just hers. So how about scaling? So what if you want to scale the x-axis by a factor of a, and then scale the y-axis by a factor of b? So our standard matrix, let's see what happens to the first basis element. Okay. So you're taking the standard, this this unit vector and you're scaling by factor A. Okay, the result would be, well, multiply that by A and this is what you get. So that would be the first column of our standard matrix. And if you scale the second standard basis by a factor of B, then you get 0B. And of course I could be scaling by negative numbers as well, right? I mean, that would just flip the vector in the opposite direction. Scaling. Okay. Let's do a shear. So what we're doing is we're kind of getting these basic transformations out of the way, and then we're going to construct some more complicated transformations using those. So shear. Oh, how do you spell shear? Is it EA or EE?
EE.
Okay, so let's see. I don't know the exact words here, but suppose you have, let's just geometry, a square, unit square, and you want to shear it like this. I guess that we would then call this a shear in the x direction. So this is what we want our transformation to be. Let's call it K. Okay, so what's our matrix? Well, this is the first standard basis element right there. When it's transformed, it remains itself, correct? It's still 1, 0. Now, the second standard basis element. So by factor k, we mean that this is now the vector k1, right? We move that over by k. This is 1. So this vector would be k1. Okay, so the second standard basis element is transformed into this vector. So the area of the unit square is 1, correct? What's the area of this parallelogram? 1. And what's the determinant of this matrix? 1. So that's shear. What else did it have? Oh yeah, and I guess shear in the y direction. Just so you know, you get in the habit of like coming up with these by just saying, that's a kind of consistent way of finding these matrices, just seeing what the elementary vectors become. So we're going to shear in the y direction by a factor k. So again, we have our unit square. And then we're going to shear this in the y direction. So by, say, amount k. So this would be k. This is still 1. Still 1. Okay. So 0, or rather 1, 0 is mapped to the vector 1k. first column becomes 1k. E2 gets mapped to itself. So it wants So now let's do like an arbitrary. So linear transformations on R2 will map parallelograms into parallelograms. So what if you don't have one of these standard transformations? But this is a problem from Strang's book at MIT. This linear algebra book. It's a house problem where you have a house and you want to find, and then you warp it somehow. So here's a house. And you transform it. Well, I guess I'll have to make this one up because I can't. I don't think I can able to read this. So. So you did some sort of transformation like this. So what would the matrix representation of this transformation be? So here we can kind of use a similar idea to finding the standard matrix using elementary, the standard basis. But we can kind of more generalize it. So we can say, well, I do know that our transformation is a 2x2 matrix. This is a transformation on R2. It's a 2x2 matrix. And I do know that it'll take this vector, like the floor of the house, and map it into this vector, correct? So this vector is 4, 0. Once you multiply it by our standard matrix, you should get the vector 6, 1. You also know that our standard matrix times the vector 0, 3 should give you the vector 2, 5. How can we find the matrix A? I mean, you have enough information, right? If you know where two of these linearly independent vectors go, you know the map. You just have to compute it. Well, let's just do this. Let's take matrix A times 4, 0. That would have to give me the column 6, 1, correct? Then matrix A times the column 0, 3 would have to give me the column 2, 5. And then we can easily use algebra to solve for A. Just multiply both sides by the inverse of this matrix to solve for A. Diagonal matrix, so the inverse is just the diagonal matrix with reciprocals, the diagonals. simplify this out, and we get 6/4. A 0, sorry. 2/3. 1/4. 5/5. Okay. And so now let's talk about the determinants here. What is the area of this house, so to speak? So we have a rectangle that's 3, 4. So it's 12 plus, this is 4 times 1. So this area is 2, right? This area is 12, so the area is 14. What is the area of this house? Now we could do stuff, we could start drawing like triangles and subtracting areas of triangles from rectangles, but we don't want to do that. Right, we can do something funky like that. Instead, we want to know the relationship between areas and determinants. Okay. So if you want to motivate the relationship, think of a unit square. Think of mapping that unit square to some parallelogram, where this is like vector AC, I guess. This is vector BD. Okay. The area of this, well, the sign area, is plus or minus, I should say, would be the determinant of the matrix. ACB. Correct? The area of the unit square is the determinant of the identity. So that's 1. This would be just the determinant of the matrix. So it looks like if you take the unit square and transform it according to this linear, matrix operator here, the area of how do I say this? So this is region R, and this is R star, where R star is just the original region transformed. We want to know the relationship between the areas. And the relationship is this, the determinant of the matrix representing our transformation. Well, it's magnitude of it. This determinant is the assigned area, times the area of the original region is equal to the area of the new region. And so, if anybody's taking multivariable, this is what we were doing yesterday with the Jacobians, essentially. You said it's the tweak factor, the stretch factor. So, using that fact, I could find the area of the new house, the warped house. So I know the matrix representing our transformation I erased. So the matrix representing our transformation, can somebody read that matrix to me?
3 halves, 2/3, 1/4, and 5/3.
So then the determinant, or the absolute value of the determinant of this transformation, this matrix, times the area of the original house equals the area of the new house. So the determinant here apparently is 5/2 minus 1/6. The area of the original house is 12, green 14. So, whatever that is, right? 14 squared divided by 6. It's 196 divided by 6. So now let's get into some more complicated transformations which are relevant to your homework. So the first one, let's say, is a reflection. Yeah. Let's do reflection about a line. So this is going to be reflection about a line in R2. So imagine we have not a vertical line. Let's just say we have y equals mx, right? So this has to be a line through the origin, by the way. Here's R2. Here's some line with a slope. Now what we want to do is simply reflect the plane about that line. And it's a little bit more difficult to see what the the standard basis elements, how they're transformed. Visually we kind of see it. It's like this would be somewhere over here, right? And transform. And reflect, you get something there. And this might be something over here, right? So it's a little difficult to work with the standard basis elements there. So here's another important approach that you're going to definitely run into when you do eigenvectors, eigenvalues. There's some vectors in this plane whose transformation is very obvious. Okay. So let's not work with the standard basis elements, but rather we pick our own vectors. So if I pick a vector along this line, can you give me an example of a vector along this line? It'll involve the n, but if x is 1, what is y? Yeah. So this is an obvious vector, 1 over n. That's on this line, or in that space. Why is this a very convenient vector to work with when talking about this reflection? Well, because when it's reflected, it stays itself, right? So we have some matrix representing this reflection, and when it acts on this vector, you get that vector pattern. Is there another vector that's that kind of, well, imagine picking a vector which is orthogonal to that one, right? Perpendicular there. And can you give me a vector which is orthogonal to that one? So some vector such that the dot product, this one and that one, gives you 0. Let's say n, so 1 times n, then -1, because then we have n minus n, we take the dot product, right? So these are definitely orthogonal. Okay. Now why is that a good vector to choose? Well, imagine picking a vector that's orthogonal to our line and reflecting it. What will become of it? It's negative, right? You're just scaling this by -1. So you get the vector. The negative of that. Negative n1. So we know that our matrix times this vector, since it's orthogonal to the line of reflection, would be the negative of that. So now we can find our matrix. Right? Because we have A times that vector column gives me exactly that column. A times this column should give me exactly that. Okay. Now we can solve for A by right multiplying both sides by the inverse of this matrix. So -1 minus n squared for the determinant in the denominator here. Flip the diagonal entries, change the sign of the opposite. So that's the inverse. Easier to look at. Okay, so we get 1 minus n squared. N, 2n, 2n, n squared minus 1. So that's given a line with slope n. That would be the standard matrix for the reflection about that line in the plane. Now your book uses a different convention. They use angle theta, right? So they define the line through the origin by the angle that that line makes with the positive x-axis. So how would you define this, the angle using our line? Well, I believe tangent of theta is m divided by 1, right? So m equals tangent of theta. I mean, tangent theta is the slope of our line through the origin. So the slope is tangent of theta. So if you replace that, let's see, what will this become? Okay, let's look at the first component. We have 1 minus n squared divided by 1 plus n squared. And n is tangent, where tangent is sine over cosine. Multiply the top and bottom by cosine squared to get cosine squared minus sine squared. Oh, okay, this works out. Of course, the denominator becomes 1. The numerator, via trig identity, gives you cosine 2 theta. And this would be, because it's just the negative of that entry, would be negative cosine 2 theta. And let's see, 2n over 1 plus n squared. And its tangent. So multiply top and bottom by cosine. You can get 2 sine theta cosine theta. Okay, so that's sine 2 theta by a trig identity. So that's the matrix that the book presented to you for reflection about a line. I'm not a big fan of this formula because it doesn't generalize well to higher dimensions, right? All right. So that's the reflection matrix for your book. Now we can take another approach here and take advantage of compositions, right? I mean, the reason matrix multiplication is defined the way it is because these matrices represent linear transformations, and you can compose transformations, right? Composing functions. And the matrix multiplication is defined in a way where a composition of linear transformations corresponds to multiplying matrices. Okay. So here's the composition of transformations. So you have a transformation with the corresponding elementary matrix A, and you compose that with B. It's going to be the same thing as the transformation of first A. Let me change that up, sorry. That's the transformation corresponding to the matrix A times B. So composing transformations is the same thing as multiplying their matrices, their standard matrices. So, if I wanted to find another way to express this reflection, think of it this way. We know the reflection about the x-axis, right? So it's not going to be hard. What we can do, let's say this angle is theta. We can rotate the plane by angle theta clockwise. So this line then becomes the x-axis, right? So we'll do that first. And what's the matrix representing the transformation? Well, it's a rotation by theta clockwise, so that's going to be cosine theta, sine theta. Let me use the notation R for rotation. Negative sine theta. Cosine. That was the rotation matrix clockwise. So let's keep track of this line, I suppose. So now that line is on the x-axis. Now we're going to reflect about the x-axis. Oh, yeah, good idea. Right, so we're going to reflect about the x-axis. Let's call it t, why not? And so that the matrix representing that was 1, 0, 0, negative. So now that so if you had a vector somewhere over here, it was here, now we reflect. And the vector is not here. And now we're going to put everything back in its original position by rotating by angle theta counterclockwise. So we're moving the line back through its original position. So now we're doing a rotation by angle theta counterclockwise. The matrix for that was cosine theta, negative sine theta. So our line is back in position and this vector is somewhere over here. And so apparently composing these three, I guess, relatively simple compositions should give us the transformation, which is the reflection about this line. So is it? So what we're doing is we're composing, we first did this rotation, then we followed that by this reflection about the x-axis. Then we rotated back by angle theta. And so this corresponds to the transformation, where if you want the matrix of this transformation, you'd simply multiply the corresponding matrices here, where this is the first matrix that was applied. So that's the matrix that's rightmost side. And then we followed by this reflection about the x-axis, so the result you get multiplied by that matrix. Finally followed by a reflection counterclockwise. Okay. So then we multiply this thing through. Yeah. Let's see what we get. Cosine, sine, sine. Negative cosine. Okay, so then we get cosine squared minus sine squared. Get 2. This is the result we get after you multiply, and then we see that using a couple trig identities. We get exactly the matrix we came up previously when defining the line by the angle theta. It's cosine 2 theta, sine 2 theta. So that's just to remind you. So when they give you this kind of sequence of transformations, right? You would probably want to find the matrix corresponding to each of those, and to get the composition, just multiply the matrices. And now here's the next transformation is an important one. It's the projection onto. Again, I don't like the formula your book gave you in terms of theta. Generalized, but so the idea now is that we're going to be taking vectors in the plane and then projecting them onto a line. So we're collapsing the whole plane onto the line. And these are called orthogonal projections. We'll just do onto the line through the origin. So we have to be, we're projecting onto subspaces, so our line has to go to the origin. So we want to take a vector and project it onto the line. It's an orthogonal projection because it gives you, the orthogonal projection would be one which minimizes the distance between the point here and the line. To minimize that distance, you can prove that, let me start labeling this now. So suppose that this is vector u. It's a vector on our line. And this is some arbitrary vector x. And I want to project, P for projection, x onto the line. So this projection has to be on the line. It's going to be a multiple of the vector on the line. And it's a projection, it's orthogonal because we want x minus this projection that way. So you take x minus this orthogonal projection, the result has to be a vector which is orthogonal to the line. That's why it's an orthogonal projection. So if you want to minimize distance between the point here and the line, you necessarily are going to have to use an orthogonal projection. This has to be perpendicular to the line or the vector here. So let's come up with a formula for orthogonal projection in R2. So let's do this. I think we're going to take a similar tack to what we did with the reflection. We're just going to pick not the standard basis elements, but very convenient vectors. So the first convenient vector, of course, would be, say, 1m, right? Like before. The projection of that vector onto the line would be itself, because the vector is already on that line. However, if you take a vector that's perpendicular, say m minus, or whatever, minus m1, doesn't matter. When you project it onto the plane, line, what do you get? It would have to be 0. Because, like, since this vector is perpendicular to the line, there's no part of this vector which is parallel to the line, right? Everything's perpendicular, so when you project it onto the line, you're going to get 0. That's the 0, 0. So knowing that, we can find the matrix representation of this projection. So we have that being mapped to itself, while this is mapped to 0, 0. Once again, we can simply right multiply by the inverse, get the matrix. So that would be the projection onto the line with slope m. And in terms of the angle theta that the line makes with the positive x-axis, that's the way you would present this projection onto a line. Again, we know the slope is tangent theta. So 1 plus tangent squared is secant squared, right? So that's going to be cosine squared. So then we have tangent divided by secant squared. So sine, cosine. Sine, cosine. And then we get secant squared in the denominator and n squared is tangent squared. So you get sine squared. Oh, get out of those. That's right. That's after just, plugging that in and reducing. So that's the projection onto the line to the origin where the angle, the line, and the x-axis is theta. Okay. So, I don't know these formulas, by the way. This is just so basic where you can just easily derive the projection that you don't need to know the formula. So So suppose, let's see, we have the line y plus 2x is z. So that would be something like this. And we'd like to project the plane onto this line. We can either try to memorize the formulas or just simply say, okay, give me a vector on this line. So if x is -1, y is 2. That satisfies the equation of the plane. And give me a vector which is orthogonal to the line. So let's say 2, 1, right? Their dot product is 0. So our projection matrix times -1, 2 will give you the same vector because it's already on the line you're projecting onto, so it's already there. Times and 2, 1, 0. It's mapped into 0, 0. So we can find this matrix. My apologies, that's minus the determinant, so it's -1 minus 4. We're finding the inverse of this matrix. Okay. So that's the matrix that does the job. Now, notice that this matrix, there's some interesting properties, right? First of all, what's the determinant of this standard matrix? You think of it this way. Imagine drawing a unit square over here. And when you project that unit square onto the line, what do you get? You get a segment, right? All this whole thing is collapsed onto this line. So we have area 0. This line here, area 0. So you expect the determinant of this matrix to be 0. This transformation is not invertible, right? Because if you have a whole bunch of vectors which get projected onto the same thing on the line, so there's no way to reverse the process to get the original vector. The determinant is 0. I mean, 4/25 minus 4/25, right? The determinant is 0. This matrix is not invertible. So what do we know about its null space? What do we know about the null space of the matrix? Well, it's not trivial, right? If the square matrix is invertible, has determinant non-zero, then there's only one vector in the null space, and that's the 0 vector itself, the trivial solution there. But here we have a non-empty, non-trivial, null space of A is non-trivial. We have other vectors, vectors other than 0 in the null space. Can you see why? Well, any vector that's that lives on the line perpendicular to the given line will be collapsed to 0. So all that whole space, that whole perpendicular line is the null space. I think for one of the problems on the homework, you're given some such matrix, and you're supposed to prove that this projects vectors onto a specific line. And how would you prove that? Here we kind of did the opposite. We started with saying we want a projection onto the line and got the matrix. In your homework, they reverse the process. They give you the matrix, and you're supposed to prove that it projects onto a certain line. Well, if you take any vector and multiply it, so I'm just pretending it's a whole new problem, or given this matrix, you're supposed to prove that it projects vectors onto this line. Well, so this matrix multiplying any vector in R2, let's see what it gives you. I mean, you're essentially, what are you finding? You're finding the column space of this matrix, right? Because the matrix times this column gives you a combination of the columns. So everything you get here must be a linear combination of the columns. So you're just looking at the column space. So how do I know that this resulting vector is in the line? Can I find the line? Again, I think the best thing to do is just look at the column space of this matrix. And how can you find the column space of the matrix? How can you find the basis for the column space, if you recall? Well, we can take our matrix and row reduce it. I should have done that. Probably the best approach. You're finding the range of this transformation. And we're going to show that the range of the transformation gives you that line. So the range of a transformation is the column space of the corresponding matrix. So we should have done that. So let's row reduce. There we go. Multiply by 5. Okay, so this is the reduced matrix. So what's the basis for the column space of matrix A? This is this column here in the reduced version of our matrix has a leading 1. So the first column in the original matrix is the basis, is a basis for the column space. So we see the column space of A is just the span of that column, i.e. it's the set of all multiples of the column. So we see that x is 1/5 of t, and y is -2/5 of t. Eliminate the parameter. And you get so we've recovered the line. That is the correct line. All right, now, if you were asked then to prove that given this matrix, that the null space is this line that's perpendicular to the given line, well, you just find the null space, or the basis for the null space of your matrix. And if this is row reduced, we know the null space would be anything where, let's say, any multiple of, say, this, if y is 1, x would have to be 2. It's a span of this vector 2, 1. So x is 2t, y is t. Therefore, x equals 2y. There you go. It's a line with positive slope 1/2, as you can see. And so our two lines have the two lines of slopes, that's the original line, that's the line for the null space. The slopes are negative reciprocals. Those are perpendicular lines. Oh, yeah. All right. Now, if we look at this particular projection matrix here, orthogonal projection matrix, what can we say about it? Like, what are some properties? Let's also write out general form. Was this n or n squared? Was this the projection matrix? And in terms of the angles, theta was cosine squared, sine cosine?
Yeah.
Here's a particular example. Okay. Of a projection matrix. What are some properties here? Well, first of all, these matrices are, what's the word? Symmetric. So orthogonal projection matrices are symmetric. And that's orthogonal is the key word. It's just a projection of And then if you want to use the language of operators, you would say that the projection operator is, I don't want to say, no, I'll just do matrices. So A transpose equals A, right? That's symmetric. And here's another neat property. What if you square these matrices? What would you get? Let's square our particular matrix, A squared. So that's 1/5, means so 1/25 plus 4/25, so that's 5/25, so it's 1/5. -2 minus 8 4 and 6 is 20. And then we can reduce that, I suppose. So what do you get? Well, you get the original matrix A. And this will be true in general of orthogonal projections, actually, all projections, not just orthogonal ones. And you can prove it using identities or something, like if I take A squared, where you're using the angle for the line. I really want to do that. No, as an exercise, just do it, right? Maybe I'll use the M. That'd be easier. A times A. Yeah, and then if you divide through, I think there's some common factors, you get the original. Yeah. That's nice. Now, why would that be, by the way? Like, why would that have to be? Okay, so imagine projecting a vector onto the line. Then taking the result and projecting that onto the line again, what would you get? The original. So once you project x onto the line, that image becomes a vector on the line. So when you projected that result on the line, you just get back the original. So geometrically, it makes sense. You just need to project once and then you're done. So that's another key property of orthogonal, or projections in general here. You don't need to know that word, idempotent, but you'd say a squared equals a. In fact, you could use these two properties to completely define what orthogonal projections are, and derive all the formulas using those two properties. And I think he can use these facts to, well, it's one of those questions that are extra practice, they're worth 0 points, but you can use these ideas to prove it. I think I wanted to prove that the null space of some projection operator, or arbitrary projection, is equivalent to the row space of is it I minus P? That's what they wanted to show. You can use these ideas, I think, to prove that. The null space of projection operators, or the projection matrix, would be perpendicular to what space? Column space of P? So can we show that the row space of I minus P is perpendicular to the column space of P? How would we do that? Well, you'd multiply these two matrices, right? Okay. Because if you take this times this, the rows of this matrix would be multiplying the columns of this matrix, right? So if I can get that result to be the 0 matrix, this means that all the rows dotted with the rows of this matrix dotted with the columns of this matrix are 0, so the rows and columns are perpendicular. So then you would have multiplied through, you get I, P is just P minus P squared. But if you're dealing with an orthogonal projection, or just projection, what is P squared? P. So yeah, you get 0. So anyway. So since the column space of P is orthogonal to the row space of I minus P, right? Somehow this shows these are equal. It does show, but I don't want to go into decomposing a vector space into the direct sum of two subspaces. Okay. We mentioned that. So is that it? Oh, for your benefit. How would you more generally come up with, like if you want to do projections onto subspaces in higher dimensional space, how would you go about that? Well, so let's just take the example of a plane in R3. Call that W for the subspace that contains the origin. And what we want to do is we want to take vectors in R3 and project them onto the plane such that this distance is minimized. How would you come up with formulas that are give you the projection? Well, you would find the basis for the subspace. So, say, A1, A2. If you had higher dimensional spaces, you would have more vectors. And you would stick those basis elements into columns of the matrix. And you would say, you realize that the projection of X onto the plane, well, it's in the plane, right? It's in the subspace. So it can be expressed as a linear combination of these basis elements. So the projection of that vector onto that subspace must be a combination of basis elements for that subspace. And of course, we can write this as matrix A times the column C, where C are the coefficients of that linear combination. Now, since we're talking about orthogonal projections, we see that we would want the vector x minus the projection of x onto the plane to be something that's orthogonal to the plane. Right? So this is x minus the projection of x. We would like it to be orthogonal to the subspace we're projecting onto. So how do we take advantage of that fact? Well, if this is orthogonal to W, then it must be orthogonal to all the basis elements of W. Okay. So we would want, so how would that, so we would want X minus the projection, right? So that's some combination of the basis elements for W. We want that to be orthogonal to W. That's the same thing as being orthogonal to all these guys, right? Because this is the basis for W. So how do you show that these are orthogonal? Well, you would take A transpose, because that would turn the columns into rows. And you would multiply by the columns of this matrix, and you'd want that to be 0. Because then you see that the rows, the vectors A, 1 through AK, are orthogonal to this. That's what we want. So we want A transpose times this to be 0. And that pretty much gives you a formula which if you do any kind of scientific computing or statistics, you will see. I'll distribute. Actually, that's just a row, my bad. Okay, and since you see the matrix A was formed by sticking basis elements and basis vectors in columns, A transpose times A is invertible. It's guaranteed to be invertible. So you can multiply both sides by the inverse of A transpose times A. And that gives you a solution for C, where C, the C vectors, all those coefficients multiplying the basis elements, which will give you the projection. So if I now multiply, A times C, I will get my projection. But A times C is A times all this business. So this is really good stuff right there. This is exactly the general way of finding the formula gives you the projection onto a subspace once you find the basis for that subspace, orthogonal projection. I believe this is used in linear regression and all sorts of stuff. It's called pseudo-inverse, I think, in some books. So if you wanted to project R2 onto a line, you see that a basis for that line would be the vector 1m, right? Because any multiple of this will give you something with a line. So apparently the projection matrix would be A transpose times A inverted times A transpose. So you get 1 plus n squared. The inverse of that is just the reciprocal, so you get a number. And you multiply this out and you get the familiar formula. Right, but what's nice about this formula is it works for arbitrary many dimensions. It's pretty powerful. All right.